Nick here, M0NTV, and welcome back to my shack and to another homebrew video, my first of 2024. Now, I've done quite a bit of building and experimenting and blowing things up, literally, and learning since the last video, and so more of that in a bit. Just to say, before we dig into what we're going to do today, one thing, the last video that I did, I showed you all the different elements of the transceiver that I'd built so far, all working together in transmit mode. And I showed you some linearity tests and the rest of it. One thing I missed though, and it was only when I was really looking hard at the 10 meter band, and I realised I'd got a spurious signal, not within the 10 meter band, but close enough to it. And a little bit of digging around revealed it was actually twice the IF frequency. So I've got the IF frequency of 13.3 megahertz, which is not great actually for 10 meters, but you know, I didn't think about that at the time. Story of my life. Anyway, I thought what I'm going to do about it, it's coming from the second mixer and it's the harmonic of the IF. So it wasn't a problem for 21 because it fell well in the attenuation of the bandpass filter, but it was on 28 megahertz. So I could have rebuilt the bandpass filter, I suppose, and something with steeper skirts. But what I decided to have a go at actually was to try a more brute force approach, which is to build a little notch filter, little LC notch filter. So this is the second version, which worked better than the first version, and that just knocks it down by 20-30 dB, something like that. So it's well down in the weeds, and it's not a problem. And I found, you know, when I put this in, it did the trick. So yeah, it just shows that even when you think you're poring over this stuff, sometimes little things creep in. So today, what I want to do is to invite you to come, if you dare, into the wonderful and mysterious world of the transmit amplifier chain. So we're going to go now and take a tiny signal and progressively make it bigger. So let me just show you now what I've got planned. And as always, I hope you find something of interest and I hope you enjoy. Now, just before we launch into what I'm going to show you next, I should just say that really when you're doing this task, it's probably best to start at the end. What I mean is with the power amplifier, and ask the question, how much power do I want this radio to put out? And depending on what the answer to that question is, will depend on the power amplifier that you use and you build. And so once you've settled on your power amplifier, then you also then need to take a step back from that and say, okay, well, what power level do I need then to drive this amplifier to get the output that I want? And so then that will then lead you to building your driver amplifier. And then you need to take a step back from that and say, okay, well, what power do I need to drive my driver? And then you compare that with the power that you've already got coming out of your radio, and that's how you do it. And if you can work backwards, then that will avoid having these big mismatches of power and thinking, oh, I need to, you know, build another amplifier and the rest of it. I'm not going to take my own advice on this occasion, mainly because I'd already built the driver that I knew I wanted to use, and because, you know, I've done it a few times, so I've got some idea of the ballpark power levels that I need to produce at different stages. But I just say that because that's really the best way of doing it, of kind of working your way back. But we're going to work the other way now, and I'm just going to show you what I built and why. So the transmit chain. So you will remember after the last video we checked what the signal was, the transmit signal coming through the band pass filters, and we were getting, it was about 650, I think, millivolts peak to peak. So let's go 500 to 700 millivolts, something in that area, about half a milliwatt and 1 milliwatt. So pretty tiny signal. Now, clearly, that is not going to be enough to drive my driver. I'm going to need much more power than that for my particular driver. So I knew I was going to have to build a pre-driver, and so this is the pre-driver I built. Now the pre-driver takes that really tiny signal, really just round about 1 milliwatt, and puts that up to, well, between 2 and 4 volts peak to peak, which is between 10 and 40 milliwatts. And that is enough then to drive my driver amplifier. And the driver amplifier will take that 2 to 4 volts peak to peak. It will send that through to the power amplifier that we're not worrying about that today. And that will produce, the driver will produce something in between 12 to 20 volts peak to peak, which is a fair bit of power. That's 360 milliwatts, right up to, well, almost to a watt, basically. Now, I'm not going to need as much power as that. And in truth, I'm shooting for about 3/4 of a watt, something like that. And I don't think I'm going to need that amount. I'm probably not going to need more than about half a watt. But I want to just give myself a bit of headroom, because depending on precisely what I do when it comes to the power amplifier, different devices require more drive than others, different configurations if I'm using 2 transistors in push-pull and the rest of it. So it all has an effect. So I thought I'd rather have too much power, because I can always attenuate it. So that's what I'm going for. So I'm going to show you now the driver and the pre-driver. So let's first of all have a look at the driver, because that was the thing that I built first, and really that has determined the other parts really of this transmit chain. Well, the design for my driver amp comes straight from the pages of this book, Building a Transceiver by Eamon, Skelton and Elaine Richards, published by the RSGB. It's still available, and I think I have recommended this one book more than any other when people ask me for ideas for resources. It's brilliant, and there's so many practical circuits that you can just pick up and use in your own build, and just some really good knowledge about how you string these things together and the rest of it. Some of the stuff, possibly some of the digital stuff, might be a little bit dated now, but that's fine. The rest of the book is absolutely brilliant, and so I can't recommend it highly enough. I am going to post my version of the schematic, because I do mess around with Eamon and Elaine's schematic a little bit, but more about that in a minute. But that's where it comes from, and this is it, or this is my version of it. Now, in the book, Eamon has 2 versions of this circuit, and I've built both of them in the past. The previous version I've built, and I have tackled this on a previous video, but that used a BJT power transistor. This one, as you can probably just see, uses a Mitsubishi MOSFET. It's an RD06 HHF1, and will produce a watt basically of power in this design. Not that you perhaps need a watt, but that's what it will do. Now, apologies, you can't see everything because I've strapped this little low pass filter board on top as I said, I wanted to kind of clean it up as much as possible. So it wasn't bad, the output, but I mean, clearly this is a linear amplifier in its own right, so really you do need to follow any amplifier when you've got some power with some kind of filtering to clear up those harmonics. So that's what I've done. The interesting thing about this is you can see these diodes here, and this resistor going across here. This is a very clever thing. This is a PNP transistor here, and you'll see in a minute when I show you the schematic. But it's essentially a safeguard, protection really against thermal runaway. This is the phenomena where the transistor gets hot. As it heats up, it starts to draw more current, and because it starts to draw more current, it heats up and it draws more current, etc., and until it burns up basically and dies. So this is a way of protecting that, and it works pretty well. I do go into the details of that in that previous video I said, because that circuitry is identical in the last one that I built. I've got it on a small heatsink, but it's enough. It doesn't even when you're running it close to a watt, it's it on sideband at least, it's not it doesn't get too hot at all. In actual fact, this whole assembly is going to be screwed down probably to the base of the chassis, so that will give it some extra heat sinking as well. And they're thermally connected, those two little heatsink bars. What else to say? The main difference with this, and I can't, if I can just show you, I'm not sure it's very easy to see really, but the main difference is just on the input and output impedance matching networks. And actually this will apply to the next thing I'm going to show you, to the pre-driver as well. I have redesigned the input and output impedance matching networks, and I've learnt so much doing this. I'm going to actually not say any more about this now, because I'm going to make this the topic of the next video, because I think it's so important, and it's been a bit of a game changer for me, particularly when you're building higher power amplifiers, to be able to get that SWR down really low. Because the thing with this was it had a pretty reasonable input SWR. I can't remember what it was now. It was under 1.5, I think, but not a great output SWR, about 2 to 1, which is not great, particularly when we're putting out more power. So I redesigned those input and output impedance matching networks, and so now I've got a 1 to 1.18 or something like that on the input, which is really good on both bands, on the 15 meter and the 10 meter band, and no more than 1.2 at the very most to 1 on the output on both bands. So that is much better. So we are wasting a lot less power. And this is going to be a QRP radio, so I don't want to spend all my time and effort generating these hard-earned watts just to have them reflected back, so that the cleaner and the better I can impedance match it, the better. So but I'm gonna, as I say, make that the subject of a separate video, how I do it, because it's not that hard. It fills a lot of people with dread, but actually it's not that hard, and I've come across some brilliant free resources that make the whole thing a lot simpler as well. So but that will be for next time. But for now, I will show you the schematic. But as you can see, there's plenty of room on this board. I could probably got it into less space really, but that's fine. And I wanted to give it adequate heat sinking. But it behaves very well. And as you'll see when we test it,
it certainly delivers the goods when it comes to the power output. But let's have a little look at it on the schematic.
Well, here is Eamon's design for what he calls a 1 watt linear amplifier, driver amplifier, and as I've put here, adapted by me. So I'm taking no credit whatsoever for all the good stuff. But what I have done is just redesign the input and output matching networks. So as I said, I have covered this basic design before, but essentially the main thing which is different about this is this circuitry here, which is an active bias network. So you see this PNP transistor here. We've got these two diodes here which are dropping between them about 1.4 volts. And the idea is that this transistor will try and keep this current the same, so as to produce the same voltage drop across this resistor here and the emitter to base junction. So if you add the voltage drop of that there to that there, it should be the same as that there. These Mitsubishi MOSFETs, I really like them. I've got to say, it's the first time I've used the RD06, but they're more expensive than your cheap IRF 510s, you know, the switching MOSFETs, but they are so much more bulletproof. I mean, they withstand great SWR mismatches, which the IRF 510 certainly does not. I know that from first-hand experience. And whilst yes, they're a little more expensive, they're not that expensive. And to be honest, after you get sick and tired of desoldering blown up IRF 510s every 5 minutes, you think actually maybe there is a better way. Well, I think it's probably here. So I do quite like these. But the main work I did was here. So essentially what I did is I used impedance matching transformer here with a capacitor which is part of my LC matching network, and I did the same here. So there's this matching transformer here, and this 1.5 nano is part of the matching network. This 10 nano here and here are just the coupling capacitors that Eamon Skelton has in his original. This seems to work pretty well, and you will see this working in just a moment.
And so on to the pre-driver, because I couldn't produce enough power from the radio to drive the driver directly, so I need the pre-driver, and this is the one that I built. And this is a design that I have used before on a number of occasions, and this comes from SV1AFN. Makis, I believe, is his name, a Greek ham, and I mean his stuff is absolutely brilliant. This comes from his website, and he freely makes his designs available on the website. I mean, he actually sells the boards and kits to build these things. I confess I've never paid and bought a kit, but I have used his designs on a number of occasions and homebrewed my own, and he's kind enough to make his designs available. I had, full disclosure, I tried designing and built a couple of my own preamps, which worked after a fashion, but nowhere near as well as this. And this only draws, I think, something like 57 milliamps, and it's only one transistor. It's one 2N3866 transistor, which I think they were literally giving them away at club sales and the GQRP club. So I got a whole load of them, and they're brilliant, absolutely brilliant. And so have a look at the website. The website is www.sv1afn.com, Sierra Victor 1 Alpha Foxtrot November.com. And you will see some of the amazing stuff he's got there on the website. Really, really good. And so there's great gain. It's pretty flat. The only thing I thought I could possibly improve on this tremendous design was, guess what? The input and output impedance matching. And so I did spend quite a bit of time on this. And I'm not going to go into it now. As I said before, I'm going to be this board is going to be our test board for that next video, where I talk about how I went about designing the impedance matching networks for this. But again, it has made a tremendous difference to the amount of reflected signal. I mean, there is virtually none with this. I can't remember which one it is now. I think it's on the RF in. It is a 1-to-1 impedance match on both bands, and not much more on the output. So it's really very effective. Now, this is completely over-engineered. Yeah, and you probably wouldn't necessarily need to go to all the trouble of doing that. But because I was kind of interested in it, because I'd never really taken it to those lengths before, I just thought, well, give it a go. And yeah, sure enough, I've managed to get some pretty good results. So again, more about that next time. So all I've done, and I'll show you MHz's schematic in just a moment, but essentially all I've done is redesigned again the input and the output networks, and actually I've got a 3 dB pi attenuator on there, just because this little design's so good, it puts out so much power. I didn't need all that, so I could attenuate it. And also you will notice on here I used a different method of construction. Can't remember what I did on the last one now. Did I use I think last time I did the Manhattan pads, didn't I, on the driver? There is one Manhattan pad, I think, somewhere here. Can't find it now. But basically, I use the kind of what I call the Dremel method, where you engrave all your little isolated pads, and then you solder down directly to those, which is a great method, but you need to know pretty much where you're putting everything before you start. You can't just start slopping the glue around and sticking pads on as you can with the more traditional Manhattan method. But it's good, yeah. And so that's that. So let's have a little look at the schematic. And here is the schematic for MHz's broadband RF amplifier. And so you'll see, I mean, there's not too much to it. There's two different kinds of feedback. You've got the emitter degeneration down here bypassed, and you've got the shunt feedback around here as well. There's plenty of attempts to choke off RF so it doesn't get into the power line. But again, the main thing that I did was I redid all this input matching network, and this is more of a proper kind of LC matching network. And here I also put a little pi attenuator on it, as I said. Oh, and I rewired the transformer, so I changed the transformation ratio, not on the primary L1 but on L2, and that kind of fits in with the other stuff I've done here. But I'll go into all of that in the next video, and I'll explain just how I came to get these figures, which make such a spectacular difference to the SWR on the input and the output. But this little thing, it's just a great design, really. And I mean, he really knows what he's doing, and I think he has I know he has a background professionally in electronics and electrical engineering, so and it shows. So this is what I built here. So now really I suppose all there is to do is to show you these actual modules that I built actually working. Now, apologies for this mess of wires here, but hopefully if you can just hear through those cables, you can see I've got the SIG gen on at 21 decimal 100 with a sine wave, and that is producing, if we come over here to the screen scope, that's producing a nice sine wave there at, well, just over 650 millivolts peak to peak, over a 50 ohm load down here. So this is really simulating what the output of my bandpass filter is on transmit. Now, the reason I'm using the SIGGEN and not using the radio itself is just that it's just a bit easier for testing purposes if I can put as pure a sine wave as possible into this amplifier, and you can see what the amplifier does to it. Whereas, you know, if I'm whistling through it and talking through it, that's not as easy to see. So, so there we go. So that is our test signal. What I'm going to do now is hook up the amplifier. Right, so I've powered up the amplifier. The RF in here is connected to this cable here, which is coming from the signal generator, and the RF out over here, well, this is the one going down to the oscilloscope. If I take you down here, first of all, you'll see on the power supply we're drawing 57 milliamps, which is very good, really, just one single NPN transistor. And if I come across to the scope, hopefully you'll see there, wow, what a lovely sine wave. About 3.7 volts peak to peak, and really nice and clean. Now, if I can, I don't know how well this is going to work. I'll try and do this. Okay, switch to the spectral display. Yeah, and you'll see it. So you can clearly see those harmonics there, but not horrific harmonics. And in any case, on the next stage, there will be a low pass filter. So that will hopefully clean up any harmonics, residual harmonics that we've got coming out of the next stage. But all in all, yeah, I'm pleased with that, and I think that's looking really good, and that certainly will be fine for driving the driver. So if we do a quick bit of maths on the calculator, so because we're using voltage, we need to do 20 log. So that's the equation, 20 log the output voltage, 3.7 volts peak to peak, over the input, which is 650 times 10 to the minus 3, which gives us a gain of 15.1 dB. Now, in truth, it's actually more than that, because if I come over here again and just remind you, you can just about see here on the output, we've got a little pi attenuator, so that's a 3 dB pi attenuator, because 18 dB was too much. I didn't need that amount, and putting the 3 dB pi attenuator on just kind of knocked the signal down so that the next stage would be happy. So that 15 dB is plenty. So yeah, really pleased with that. Works really well. So I've now I've run the cabling around another way because I haven't got enough room on the bench there. So we've got the pre-driver. So I'm feeding exactly the same signal as we did before into the pre-driver, but now the pre-driver is feeding into the driver, and you can't actually see because of the filter on top, but it's feeding into there. And actually what happens is we send the signal comes out of the driver here, then goes through this 30 megahertz low pass filter, and then goes back out down this end and then feeds back through to here. And then that, of course, is going through to the 50 ohm load and the scope. So I'm going to power it up and we'll see what we get. It helps if you power up the right one. That's a problem with having dual linear power supply. It's a 50-50 chance. There we are. So there we go. Well, yeah, just over 18, let's call it 18 volts. And lovely, and you'll see what a lovely looking sine wave that is, and that's of course in no small part due to the low pass filter. When I had it without the low pass filter, it was pretty good, but there were some more harmonics, as you might expect, because I mean this is actually a linear amplifier in its own right, and so you'd really want to kind of have some filtering after that. But that, yeah, does a lovely job. So I think if I can just do the same here. And you'll see, yeah, and wow, what a great job that does of getting rid of any of the harmonics there. So yeah, all in all, really pleased with that. That should do just fine. Now, just for completeness sake, having the radio here, I've got to actually switch the radio on. So we're on 21.100 as usual. But this is now, the SIG-gen's off, this signal's now coming from the radio. It's actually coming out of that little bit of coax there, coming around the back. It's coming to, that's the notch filter that I mentioned. And then going in to the pre-driver and the driver. And okay, we'll come around here, let's move this microphone out of the way if I can. And try and balance this. Very high-tech stuff here. Okay, let's key up the PTT. 1 2, what 1 2, 1 2, what 1 2, what 1 2. Hello, hello. You see, we're even peaking 20 there. So that, I mean, that's fractionally under a watt, really. So a little bit more than we had when we were testing with the SIG-gen. So yeah, well, that's fine, more than enough. And almost certainly I'll be attenuating that down a bit because it's highly unlikely I'm going to need that level of drive, depending what I do with the PA that I end up using. But it's good to have that headroom and the opportunity to have that. So hang on, let me just whistle into this for a minute. Right, okay. And if I show you on the spectral display, 1 2 1 2 3 1 2 3 1 2 3, and you can see, yeah, that's nice and clean, and it looked clean when you saw that sine wave. So yeah, great, and that'll be fine. And you know, I wanted to get as clean a signal as possible going into the final power amplifier, and we'll filter up the final power amplifier as well. So it should be well on course. Finally, I thought I ought to do a bit of a test on 10 meters. Funny, I'm so used to building single band rigs, I keep forgetting I've got 2 bands here, which is half the problem with the taking me off the ball with the spectral purity on 10. But anyway, so there we are, 28.1, and let's come down here and put this on here. Hello, 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 1 2 1 2 1 2 1 2 1 2. Okay, so now I think we're getting up to, well, about 16 I think we're peaking at. Yeah, high 15s, 16 volts peak to peak, which is obviously not going to be as much as on 21 megahertz, as you might expect. But that's not bad. That's not too bad at all. So yeah, we'll call that, I think we'll call that 16. Let's be optimistic. Call it probably goes to the 15 or 16 really, but yeah, we'll call that about between 15 and 16 and call that quits. So just by way of recap, you'll see here from the bandpass filters, we are getting 650 millivolts peak to peak. That is a signal level of just over 1 milliwatt. So I'm putting just over 1 milliwatt into the pre-driver, and the pre-driver is giving me 3.7 volts peak to peak, 650 millivolts in, 3.7 volts peak to peak out. That equates to 34 thereabouts milliwatts. So that gives me an overall gain of 18 dB, But you'll remember, because I've got a 3 dB pi attenuator in there on the output, then I'm knocking that down to 15. So the 34 milliwatts, the 3.7 volts peak to peak, then is fed into the driver, and the driver is giving us, and these are all on 21.100, and the figures are lower as we've seen on 28. But I wasn't going to go through the whole thing on 28 as well. But so yeah, we're getting 18 volts peak to peak. That is 810 milliwatts, and as you saw, we're actually getting a bit more than that. So that can definitely come down, and that's a gain of 13.7 dB. So that's what it looks like. I reckon probably we're not going to need more than about, well, half a watt probably on to feed the power amplifier, depending on what transistor I use and you know what configuration I use. So, but that's fine, because there's space actually on this board to attenuate down further, and almost certainly I will be doing that to bring it up. But it gives me a bit of headroom here, so it's great. And certain devices require higher gain levels than other ones, so at least I've got enough room to maneuver. So yeah, so that's it.
So there you go. Driver and pre-driver are done. Fantastic. One thing I often do, and I did this time, before actually I ever even get around to firing up the soldering iron, is I will usually noodle around, as Pete Giuliano would call it, with LTSPICE, the electronics simulation software. It's free. It's absolutely brilliant. It's very powerful, and actually surprisingly accurate in what it predicts. So I often use that and play around with that, and before I commit to actually building anything. So if you're interested in that, what I've done, linked below this video, I've put my schematics to the driver, the pre-driver, to the notch filter, and to the low pass filter. But I've also included the LTSPICE simulations for those 4 circuits, so you can have a little play around with those as well. Do like and subscribe if you've enjoyed this video, and if you've got any questions or comments, I'm not an expert of course, but I'll do my best, then please leave those below. I hope you found something of interest here. The next video, as I've said, is going to be a good one. Well, you'll have to be the judge of that. I'm quite excited about it, just because I think it's really interesting. The challenge of designing and building an impedance matching network for an RF amplifier without getting bogged down with loads of complicated mathematics and stuff. So yeah, looking forward to that one. But until then, thank you ever so much for watching. Look after yourselves, and I will see you on the next video. 73. Bye-bye.